So, in this course you are going to learn about Industry 4.0 and Industrial IoT IIoT. So, we will get into the depth of each of these in detail throughout the course. However, let us first try to understand what is central to each of these technologies. So, IIoT is Industrial IoT, which is about the applications of IoT in the industry. So, there are some industry specific requirements for which the existing IoT technology, which have applications in different domains, will have specific requirements of industries and will have to be tailored to cater to those industrial requirements. So, that is where Industrial IoT comes into picture and is so much popular, particularly in the industry nowadays. Most of the industries globally, they are transforming, they have been mandated to transform to be Industry 4.0 compliant, and they are transforming towards the adoption of IIoT technologies. So, we will be learning about the different aspects of each of these Industry 4.0 and IIoT, but first let us try to understand what is IoT. So, very briefly, IoT is about Internet of Things, a technology which tries to build up an internetwork of different things. And what are these things? These things are different physical objects that we use, that we see around us, and so on. These physical objects could be anything and everything that we can think of, starting from things like the toothbrushes which we use very early in the morning, to the air conditioner of the room, to the heating system, the projection system in front of us. And this also includes the traditional computational devices such as computers, PDAs, laptops, and so on. So, computational as well as the traditional computational devices plus the present different physical objects, all these objects that I mentioned, like the toothbrush, projection system, heating system, this refrigeration system, and so on. So, all of these things would be internetworked, would be interconnected, and then this internetwork is going to send lot of data which will have to be processed in order to make use out of the data that have been retrieved. So, there are different uses of it. So, IoT finds applications in building smart homes, for instance, smart cities, and so on. So, there are even different components of smart cities like smart transportation, smart parking, smart healthcare, and so on and so forth. So, IoT finds applications in making cities and homes smart. In the industrial context, we are trying to think about an extension of all of these to serve making industrial processes much more efficient and autonomous. So, we will look into each of these. Now, before we do that, in this lecture, let us try to understand that what is central to the IoT or IIoT. So, what is central are basically certain things known as sensors and actuators, and there are few other associated peripheral technologies also, which we will cover in subsequent lectures. But sensing and actuation is key to IoT as well as IIoT, right. So, let us try to understand what is this sensor and what is this actuator. So, before we do, we need to understand that both sensors and actuators can be classified as transducers. So, these are like transducers. So, sensors, actuators are transducers. So, what is a transducer? So, transducer basically is something that converts the signal in one form into a signal in another form. So let us look at this diagram in front of us. So, we have over here we have a sensor, we have an actuator. So, this sensor plus the processor, which will basically process the input that is coming from these sensors, this is a transducer. So, this is a transducer. Similarly, actuator plus processor is also a transducer, right. So, as you can see over here, this transducer and the sensor inside it takes some input signal and produces certain output, sends certain output, which will be processed further, and based on the processed data there will be something that will be actuated. So, all throughout, as we can see, there is some kind of energy transformation that is happening, and this actuator then produces certain output. So, this is how sensors or sensors or actuators as transducers work. So, let us look further. So, we have the concept of transducer, which, as I said, is some device which converts a signal from one physical form to another physical form, and these physical forms could be like electrical form, mechanical form, magnetic form, thermal, chemical, optical, and so on. So, what we are seeing is that a transducer is nothing but an energy converter. It converts the energy from one form to the energy in another form. So, for instance, things like microphone, the traditional microphone. The microphone basically converts sound signals to electrical signals, which basically are then amplified further, and the speakers, basically through the speakers we are able to hear, right. So, this is basically the concept of how a microphone works. So, microphone is an example, a traditional example of a transducer. A speaker is also likewise a converter of energy from electrical form to sound. So, a speaker is also another example of the transducer. Similarly, we have antennas which will convert electromagnetic energy into electrical energy and vice versa. So, antenna is also a transducer, and there are many other examples such as a strain gauge, which is also an example of a transducer. So, let us try to understand sensors as transducers. So, what is that sensor? Sensor, as this name suggests, senses something. Senses what? Senses the physical quantity, the physical changes, the physical characteristic of the environment in which it is operating. So, a temperature sensor, for example, will sense the changes in the temperature of the environment in which the sensor, the temperature sensor, has been deployed, is operating. So, this is an example. So, it is basically the characteristic of a device or material to detect the presence of a particular physical quantity, and in this particular example that I have given you, this physical quantity is this temperature. So, the changes to detect the presence, the change in the temperature is what a temperature sensor would do. So, the output of this sensor is a signal which is converted to some human readable form, and these human readable forms can be different forms, changes in the current characteristics, changes in the voltage characteristics, changes in the resistance, changes in the capacitance, changes in the impedance. So, these changes are understandable by humans. So, this is this human understandable or readable form that is referred to over here. So, a sensor basically performs some function of input by sensing or feeling the physical changes in the characteristic of a system in response to some stimulus. So, these stimulus are basically physical parameters. These stimulus could be changes in the temperature, changes in the lighting condition, changes in the gas. So, these gases could be like a gas sensor, for instance, would sense changes in different gases for which they have been fabricated to sense. So, for example, there could be a methane sensor, methane gas sensor, a carbon dioxide sensor, carbon monoxide sensor, oxygen sensor. So, these are basically sensors which have been devised to sense the changes in the amounts of these gases in the environment, right. So, gas sensors are basically incidentally very much useful to monitor different presence of different gases, particularly in our current context of environment monitoring. Gas sensors are very useful. They are also very useful for mining environments. So, for example, methane sensors are used in the mines to detect the increase in methane gas, possible increase in methane gas in coal mines. And as you know that these gases are very dangerous. So, it is very important. So, IoT in mines, for example, you need to use different gas sensors, right, if it is for gas monitoring application. So, these sensors are very much useful. So, temperature, pressure means atmospheric pressure, atmospheric temperature, or it could be temperature of any particular object. So, all these different sensors could be used for this particular purpose. So, then we have that something is sensed and the response is in the form of some changes in the resistive capacities, changes in the capacitive capacities and so on, or changes in current voltage characteristics. So, all these characteristics, current, voltage, resistance, capacitance, impedance, so all these, so these come as in the form of the output. So, here are some pictures of certain sensors, and these are the ones, the sensors actually that I have in my lab, and there are many other sensors also. I picked up these ones in order to show you how different sensors look like. And these are not the only ones, actually the sensors basically they come in different shapes and sizes. So, there are some, these are like macro sized sensors, but you could also have micro sized sensors which are like MEMS based sensors. There could be nano sensors also. So, these are like even more advanced kind of sensors that are available, and these sensors have different purposes. So, this is a temperature and humidity sensor. This is a gas sensor for detecting LPG gas, methane, carbon monoxide and so on. This is an ultrasonic sensor. This is a camera sensor, you can see the camera over here, camera sensor. This is PIR sensor, this is rain detector sensor, and this is fire detector sensor. So, you have so many different types of sensors. Now, let me see if I can show you some of these different sensors. So, this is a PIR sensor. Okay, this is a PIR sensor, and we have this is a ultrasonic sensor. This ultrasonic sensor can help you to detect how far a particular object is. So, this sensor can help you in that. So, obstacles, basically obstacles can be detected with the help of this sensor, and this basically works on the basis of ultrasound, a sound wave that is sent from one of these two cylinders that you can see over here. So, one cylinder sends a sound signal, it gets reflected by that obstacle and is detected by the other, and then based on that this entire sensor works like how far a particular obstacle is, where if there is an obstacle in its range and so on. Let me show you another sensor of different type. This is basically the color sensor. It can detect colors, different types of colors. This is an accelerometer sensor, accelerometer. Then we have the gas sensor, carbon monoxide more specifically. This sensor can detect carbon monoxide gas. Then I have also brought for you another sensor which is the rain gauge, right. So, rain, basically rainfall sensor, this will detect the rainfall, right. So, we have different sensors. Now, let us go back to our discussion what we were having earlier. So, we have these different types of sensors. These sensors have their own different ways of operating, but let us try to understand first the characteristics of sensors at a very high level. In general, the characteristics of sensors can be classified into two types, the static characteristics and the dynamic characteristics. So, before that, let me try to tell you about how a particular sensor works. So, different sensors have different operating mechanisms, but in general what happens is after you have a sensor starts its operation. So, it takes a while in general, not necessarily, in many cases it will take a while to come to something called the steady state. So, it will come to a steady state of operation and then it will work in that steady state. So, static characteristics basically are about the characteristics of a particular sensor in the steady state condition. In the steady state, once the sensor has come to its steady state, in that steady state how the output of a sensor changes in response to the input change, and dynamic characteristics are before that. So, these dynamic characteristics are about the properties of the system's transient response to an input, right. So, before basically the sensor achieves the steady state, this is what it captures. So, these static characteristics could be characteristics such as accuracy, and as this name suggests, it is about the correctness of the output compared to a superior system, how much accurately, in other words, how much correctly, how much accurately the sensor measures whatever it is supposed to sense, right. Then we have another characteristic, a static characteristic, which is the range. Range means the range of operation, lowest value to highest value. How much is the range of operation of a particular sensor? Lowest temperature to highest temperature of a particular temperature sensor is the range of that particular sensor, right. Then we have resolution, and resolution is about the smallest change in the input that a sensor is capable of sensing. Smallest change, the resolution, like the resolution of a camera for instance. Similarly, you have the resolution of a sensor like a temperature sensor. So, smallest change in temperature for instance, that a particular temperature sensor is able to sense or detect is basically the resolution of a particular sensor. Error is basically the difference between the standard value and the value produced by the sensor, that is the error characteristic. Sensitivity indicates the ratio of incremental change in the response of the system with respect to the incremental change in the input parameter, right. So, that is basically the sensitivity of a sensor. Then the linearity characteristic is about that the deviation of a sensor has in its value from the straight line curve. So, if you draw the curve of behavior of a particular sensor, so the deviation it has from the straight line is the linearity characteristic of a particular sensor. Then you have the characteristic like drift. Drift is about that if you keep a particular sensor for long duration of time in a particular temperature, for if it is a temperature sensor or any other sensor, for a particular reading condition, if you are keeping it for a sufficiently long duration of time, then the difference in measurements that it will show over the period of time is the drift. Then we have the repeatability characteristic, which is the deviation from the measurements in a sequence under the same conditions. So, whether the same value can be repeatedly obtained under the same conditions by the same sensor is basically the repeatability characteristic of that particular sensor. Now, let us come to those were the static characteristics. Now, let us come to the dynamic characteristic. So, dynamic characteristics is about if you are changing the inputs, how well the sensor responds to its changes in the input. So, the transients that are received are captured through the dynamic characteristics. So, you have different things like zero order system, which is basically a system where the output shows a response to the input signal with no delay. And these zero order systems do not include energy storing requirements. So, basically a potentiometer, for instance, measures the linear and rotary displacements, right. So, this is an example of a zero order system. First order system are when the output approaches its final value gradually. This is first order. Gradually is very key to this particular thing, the first order system. And these systems will have some kind of mechanism for energy storage and dissipation, both, right. So, typically let us say there could be a capacitance, for example, a capacitor which will store this energy and dissipate over a duration of time in these systems. Second order systems will have complex output response, not gradually, but a complex output response, and this output response of these sensors will typically oscillate before the steady state, right. So, it will be something like this. It will be something like, if you are plotting, then it could be something like this before that steady state is arrived. So, this oscillation between certain values, right. So, these are basically for the complex output response of these systems. These are the second order systems. Now, let us look at how these sensors could be classified. The sensors could be classified in different ways. They could be classified as either passive sensor or active sensor, analog sensor or digital sensor, scalar sensor or vector sensor. So, let us look at what are these. A passive sensor cannot independently sense the input. So, examples of passive sensors are accelerometer, soil moisture, water level, temperature sensor, and so on. But active sensors are the ones which can independently sense the input. For instance, radar as a sensor is an example of an active sensor, a sounder, altimeter sensors, and so on. Then let us look at another classification, analog versus digital. So, analog sensors, again as this name suggests, produces output which is some continuous function of the input parameter. Examples would be temperature sensor, light detection sensor, LDR, pressure sensor, analog pressure sensors, the analog variants of these pressure sensors, analog Hall effect sensor or magnetic sensors, and so on. A LDR shows continuous variation in its resistance as a function of intensity of light falling on it. Digital sensors are basically the ones where the response is of binary nature, and these have been designed in order to overcome some of the limitations of the analog sensors, which produces continuous function of the output with respect to the input change characteristics. So, there is some analog to digital conversion that is there in most of these digital sensors. So, examples of digital sensors would be PIR sensor, digital temperature sensor, and so on. Scalar sensors and vector sensors. Scalar sensors are basically the ones which will measure only the magnitude of the input parameter, only the magnitude. Basically it is the difference between scalar values and the vector values, which basically shows the difference in the scalar sensor versus the vector sensor. So, the response of a sensor is a function of the magnitude of the input parameter, only the magnitude of it. So, nothing else, and these are not affected by the direction of the input parameter. So, examples of it would be temperature sensor, gas sensor, strain sensor, color sensor, smoke sensor. These are all examples of the scalar sensor, because the detection of these parameters do not depend on the change in the direction of the input. change in the direction of temperature, change in the direction of gas, etc., etc. It does not get affected by that, but the quantity of the temperature, quantity of the gas present, and so on. Then we have the vector sensors, which are basically the response of the sensor depends on the magnitude, the direction and the orientation, not only the magnitude, but also the direction and the orientation. Examples would be accelerometer, gyroscope, magnetic field, motion detector sensors, and so on. So, let us look at how an actuator basically works. So, as you can see in this particular figure, an actuator takes two inputs. One input is the energy. So, there has to be some kind of an energy supply, energy source, and some signal, and together these will be taken by the actuator to produce some kind of a motion, such as the force or whatever. So, an actuator is a part of the system that deals with the control action that is required, the mechanical action. So, typically mechanical, but this could be mechanical or electromechanical and so on. So, we could have mechanical actuators or electromechanical actuators and so on. So, let me now show you some pictures of actuators that I have in my lab. There are many others, but these are some of these pictures of actuators. So, this is an actuator. This is an electric relay. So, this relay, what it does is it transforms the electrical energy into some kind of mechanical action. So, or it could be electromechanical as well. So, these relays are very much useful for performing, taking an electric signal and performing some kind of mechanical mechanical operation, such as turning on a particular valve, turning off a valve, turning on a device such as a compressor, turning off a device such as a compressor, and so on. So, this is a relay, which is an actuator. Then this is a motor, a DC motor. This is a DC motor, as you can see over here. This is a DC motor, and this motor is also an actuator, and you know what a motor does. So, this is one motor. There could be different types of motors, and each of these is basically an actuator, examples of actuators. And let me show you another actuator, which is basically another type of motor, which is known as the stepper motor. So, this stepper motor is also an example of another type of actuator. You could also have actuators like these, which I think most of you have already seen, right. So, you have these could also be actuators, right, and you know what it is, these are the LEDs. So, an LED could be turned on or off in response to something being sensed, let us say a gas being present. So, you turn on the LED. So, that becomes an example of an actuation. Okay. So, let us now go forward. So, an actuator basically what it does is it takes a control signal as an input and also the input of some energy source, and then it performs its operation. So, here is the picture of a DC motor, and I already showed you live the how a DC motor looks like. Similarly, a relay is another example, electric relay. These are different examples: electric motors, solenoid valves, hard drives, stepper motor, comb drive. Then you have hydraulic cylinder, piezoelectric actuator, pneumatic actuators. These are different types of actuators, and these actuators can come in different shapes and sizes. These could be micro actuators, macro actuators, and so on, depending on the size of these actuators. So, the actuators can be classified into different types, and these are some of these examples: electric linear, electric rotary, fluid power linear, fluid power rotary, linear chain actuator, manual linear, manual rotary. These are some different types of classifications of actuators. Now, let us look at this electric linear actuator. So, as this name suggests, these are basically powered by electric signal. These actuators are powered by electric signal, and these basically that electric signal, electric energy in these actuators is transformed to achieve some kind of linear displacement, and that is why these are known as electric linear actuators. These could be examples could be electric bell, and this is the picture that you can see, the animated one. So, electric bell, opening and closing of dampers, locking doors, braking machine motions and so on. These are examples of use of electric linear actuators. Then the next one is electric rotary actuator. So, an example is what you see in front of you now. These are powered by electrical signals. These are powered by electrical signals and converts the electrical energy into, as this name suggests, the rotational motion. So, the previous one was electrical energy into linear displacement, and this one is electrical energy into rotational motion. So, quarter turn valves and different other electrical motors, for example, these are all examples of electric rotor actuator. Then you have the fluid power linear actuator, and again as this name suggests, these are powered by different electric fluids, hydraulic fluids, gas or air pressure and so on, and produces linear displacement. Then you have fluid power rotary actuator, again powered by fluid such as gas, liquids and so on, but produces rotational motion, like the example that you see, the picture that you see in front of you. Rotational motion is produced as an output of these actuators. Then you have the linear chain actuator, which basically consists of devices, mechanical devices such as sprockets and sections of chains, which produce linear motion by the free ends of the specially designed chains, and the picture is in front of you in order to understand how these work. So, these are primarily used in motion control applications. Then we have the manual linear actuator, which provides linear displacement through the translation of manually rotated screws or gears. So, here basically it is not automatic, here it is manual. So, manual rotation is performed on some screws or whatever, and consequently there is some linear displacement. So, these are the manual linear actuators. So, these are examples of these could be found in gearboxes, hand operated knobs, wheels, etc., and these are primarily used for manipulating tools and workpieces. Then you have the manual rotary actuators, which provide rotary output through the translation of manually rotated screws, levers or gears, and these are primarily used for the operation of valves. So, with this we come to an end of this particular lecture on sensors and actuators, and as I told you at the outset, sensors and actuators are basically key to the building of IoT and IIoT based systems, and everywhere throughout you will see that in this course we are talking about the use of sensors and actuators, and this preliminary understanding about each of these, the sensors and actuators, is necessary for you to have an in-depth understanding about how IIoT works. So, these are some of these references in front of you. There are many more to be there, but I think these will be sufficient, and whatever I have discussed is sufficient for you to have the basic understanding to go forward and understand the other lectures in this course. Thank you.